Hi guys, welcome to another video in the Network Fundamentals series. Today we're going to talk about Layer 2 and Layer 3 concepts and also touch on ARP, Address Resolution Protocol, and VLANs, which are two concepts that can play into how Layer 2 and Layer 3 forwarding and concepts can actually really be understood. So before I get into it, I'll just quick refresher to remind us of the OSI model, because it's really important to understand these things when you're speaking about the fundamentals of Layer 2 and Layer 3 addressing. So remember that as we pass traffic down from an application down onto the network, down towards the physical media, we're adding these headers which contain control information. So at Layer 3, that control information would be like IP addresses, and at Layer 2, that control information will be things along the lines of MAC addresses. And so we'll get onto what that means later. But it's really important to remember that some devices, certainly inside the networking world, will only process some of this control information. It'll only go up to, for example, it'll only go up to Layer 2 to read the information at Layer 2, that control information. And then it'll just pass it back down the stack once it's understood what that control information is and made a decision around it. Other devices may go up to Layer 3, 4, 5, 6, 7, whatever. But most of the devices that I'll be talking about are routers and switches, which mainly work at Layer 2 and Layer 3. So now that I've just recapped that, let's jump into Layer 2. And so why do we need it? Well, Layer 2 is really looking at, if you remember back at the OSI talk that I did previously, it's looking at the local segment. So how you connect inside your local network. So to give a practical example, that would be how I connect from my laptop to my home router, or if you're in the office, how you would connect between your PC and a test device in a server room, or how you would connect from your device to the router ready to go out onto the wider internet. So you're really looking at a local portion rather than the wider scope of going across the internet, for example. So in this small example, Layer 2 addressing is really focused on how we can move between device A to get to device C, for example. And so in generic sensors, what would happen is if we didn't have this switch, if this didn't have any logic, to get to C, A would send traffic to the switch wouldn't know any better, and it would forward the traffic out of all of the interfaces if it had no logic, right? And sure, that would get the traffic to C, but also B would get the traffic as well, and D would get the traffic, and it doesn't need to get that traffic. So that adds extra load potentially on the switch, and it adds extra processing power required on B and D to process that message and see, is this actually destined for me? Now, nowadays, that's not too much of an issue. The devices that we work with are highly powerful. They can manage a few extra packets. But if that few packets becomes millions of packets, then you can very quickly become overloaded. So that's why it's really important for a local layer network to know where it's actually going to send traffic to. It doesn't want to flood the traffic unless it actually has to. So what we use is a concept called media access control addresses. So it's controlling the local media, which is Ethernet in this situation. In this basic example, it could be anything. It could be Wi-Fi, it could be frame relay, it could be ATM. But focusing on more modern technologies, in this situation, it's going to be Ethernet. And because we've got a dumb switch or a Layer 2 switch, we're really focusing on the Layer 2 network. So we want to be able to say, okay, within my Layer 2 network, inside my Layer 2 domain, because we're only working at the Layer 2 level of the OSI model, I need to know how to actually address to get to C. That means that the switch needs to know where C is. It needs to know what interface it's out of and how to actually get there. So that's why we have those addresses, to make sure that we can actually send the traffic to the right host. Sure, we can use IP addresses at the Layer 3 layer, but obviously then these end devices would then have to process all of that information and do a level of processing to understand, okay, this actually isn't for me, this isn't my IP address, discard it. So to make sure that we don't have to go through that processing, we use these addresses. And so those addresses are split up into two portions. We have a organizational unique identifier, and this represents a well-known reserved address space for specific companies or manufacturers. So that could be Cisco, that could be Asus, that could be Lenovo, that could be whoever produces some kind of physical hardware or virtual network interfaces. They should have some kind of globally unique identifier to say, this MAC address is from Cisco, for example, or this is from Asus. And those MAC addresses are then assigned to physical interfaces or virtual interfaces. Now, the second portion is intended to supply a block of addresses for those specific devices that this manufacturer would produce. And so the intention here is that the manufacturer would control how that is generated, how that is assigned in such a way that it should be globally unique. So the theory is that you should never see the same MAC address more than once. But obviously that isn't too much of an issue if you do over the scope of the world. Obviously, if you see the same MAC address within inside a local scope, within inside our local network, our layer 2 domain, well, that's going to cause issues. But probability suggests, with the way that these things are processed and assigned, that you should never see something within inside the same local domain more than once. So that second portion, this 9389 F9, is a random assigned set of values. And these values are, while they look like they might be in normal 1 to 9 or representing 10 values, they're actually in base 16. So what's called hex digits. And so they represent, from 0 to 9 for, 10 values, but then they also expand up to, I want to say F, F. So you've got A, B, C, D, E, F. And so that just allows you to represent a bigger space of data or a bigger value within inside a smaller representation. And in theory, while we're seeing this in hex, you could just see this in binary. You could see this in the raw 0 and 1s, but it was decided, well known, that we would use hex to represent MAC addresses. Now, I've mentioned the first portion, the second portion. They are then put together, and then they are used when we are sending and receiving data at that L2 or layer 2 portion. So how does that actually look like on a network? So bit of a rough diagram here that we'll use throughout this presentation. But let's say we have a tech network. This is running with inside a layer 2 domain. We then demark that layer 2 domain or end that layer 2 domain when we hit a layer 3 device. In this case, it's a router, which will have the ability to look at the layer 3 information and move between different scopes, so between a layer 2 network and another layer 2 network. Now we'll get onto what that actually means and how that looks a little bit later, but just to give you that concept, this tech network would be one layer 2 domain. This then sales network would be another layer 2 domain, and then this lab network would then be another layer 2 domain. And so we'll get onto what IP addresses actually mean in that sense, but just try and remember that as I'm going. So, cool, we've got these MAC addresses, but actually, how do we know what that actual MAC address is? So if we, yet again, look back to that OSI model, the way that traffic will flow from application to end device is that application should know a specific destination IP address. It should pass that down the stack. Maybe there's different processes within inside your application, which then just passes it down to a different process, and that process then knows what IP address to send it to, regardless. As you pass down the stack to layer 3, you should at that point know the destination IP address is going to be X. So in this case, it's going to be destination IP address of 10.12.3.2. And that's great, right? But this device, C, which is sending that data, it doesn't know what physical address or what MAC address is going to be required to reach that IP address. So sure, it could send it out onto the network as a broadcast packet. That would eventually get there, but it's obviously inefficient. As we mentioned previously, B would still get that traffic when it's not destined for B, it's destined for A in the end. So we have this process called Address Resolution Protocol, or ARP. And what that does is it matches up, tries to translate an IP address to a physical MAC address. And so we do this by using some kind of control messages that are sent across the network. And in this case, it is an ARP request. So what this ARP request is doing is it's saying who has this specific IP address on the network? Who has 10.12.3.2? I don't know the physical address, so I need to know who it is or where to get it. Now that is sent with relevant IP addressing, and it's also sent with a source MAC address and a destination MAC address, which is a broadcast address. Now that broadcast address is used because, well, no one knows where that actual destination physical MAC address is, so it's going to flood it just across its network. Now, sure, that is inefficient, but what we'll later do is we'll cache those records between a MAC address to an IP address, so we don't need to do this constantly. Anyway, C has just sent that ARP request. That's then received at this layer 2 device. That layer 2 device isn't going to care about the destination IP addresses or the source IP addresses, but what it's interested in is its destination MAC address and source MAC address. Now, in normal operation, this switch will actually look at the layer 2 information and it will see the source MAC address and it'll say, well, I haven't seen that source MAC address before. Let me actually cache that just in case I need it in the future for some reason. So it's going to see, well, what interface did I receive it on? Well, in this case, we're going to assume this is ETH1.3, for example. So that switch is going to assign that MAC address to that specific interface. Well, it's going to relate that. Sorry, it's not going to assign it. It's going to relate. So it's going to know that physical MAC address here, ending in 89F9, is out of that specific interface. So if you want to reach it, send your traffic that way. Cool. It has that cached for the future, but that doesn't matter in the case of ARP. ARP still needs to then broadcast that ARP request. So the switch notices the destination MAC address. It sees it's all Fs, which is the last MAC address that is physically possible, and it broadcasts it. It knows that that is a broadcast MAC address, and it sends it out of all of the physical interfaces other than the one that it's been received, obviously. And so B receives that ARP message. A receives that ARP message as well. So B is receiving a message saying, are you 10.12.3.2? In this case, no, it's 3.3. So that effectively ignores it. But what that host does at the same time, so it learns for the future, is it processes all the way up to layer 7, right? So it's processing layer 3 as well. At that layer 3 network layer, you've got the source and destination IP address. Because we have that populated, we can say, okay, we've got a source MAC address, we've got a source IP address. Host B can then do its own ARP cache. It doesn't have to then request in the future who is 3.4 because it's already then cached it from this original ARP request. So it matches this source MAC address of the packet that it's just received with then this source IP address to then form what's called an ARP table inside its local host. Now that usually happens. In some cases, maybe it doesn't, but usually on probably 99% of normal devices, it will start to form this ARP table, mapping between these physical addresses and these logical addresses. The physical address being the MAC address, the logical address being the IP address. And what it's also doing, very similar to the switch, and I didn't describe it here because we're just giving the example of a simple PC, which might just have only one physical interface. But what it's also doing in itself is it's caching that MAC address to the physical interface that it's just received that traffic as well. So in the case of, let's say a server, it's received this ARP request out of from the first interface, then it's going to map that first interface to that specific MAC address, or sorry, the reverse. It's going to map the MAC address to that physical interface. So it's going to know that physical interface ending in 89F9 to the outgoing interface that it's just received that ARP request on. So anyway, B isn't interested in this ARP request because it doesn't have that IP address, but it has cached all the information so it can process that in the future. However, A does receive this request and it knows that it is actually for it itself. It does the relevant caching that we just discussed that B does as well, so it has that information for the future. But what it's also then doing is it's doing an ARP response. It's saying, hey, that's me. I'm 10.12.3.2. And as a result, it's then sending back an ARP request with the relevant details. So it's source IP address, destination IP address, all the way back down to C. It's also then setting the source MAC address and the destination MAC address. Yet again, that hits the switch. The switch then does its normal MAC address caching. It says, okay, we've received it via this interface. It has this source MAC address. Let's cache that. Let's start forming this table of MAC addresses against physical interfaces. That then gets forwarded out because the switch already knows this destination MAC address is out of this interface. So it sends this ARP response out of this physical interface towards the host of C, and happy days, C then receives it. It caches this source MAC address that was responded with to that logical IP address. At that point, C knows then the destination MAC address, and we can actually pop that in our data that we want to send, and it can send it on its way. So that's ARP. Hopefully that made sense. A little bit of technical detail there, and also talking about some of the caching that can go on. Now, obviously this happens at startup. Once you start to cache things as you go on, as you start to transmit data across your network over time, these caches fill and fill and fill, and you rely less on things like ARP caching because you already have the state stored and you can refresh that state over time. So what does that normally look like? What does that normal data flow look like? Well, so A in this instance has some data that it wants to send. It wants to send it to the destination of 1.2 in this situation, which let's assume it's C. I really should have used consistent addresses. Sorry about that. It wants to send it to 1.4, which is going to be C. It'll do an ARP lookup and it'll say, okay, I'm going to look at my ARP table and see what physical address does map to that logical address of 1.4. Well, it's the address of all C's, C, so on and so forth. Just want to iterate here. These specific MAC addresses are generic. They are not real examples. They are fictitious for this example, just so it's really clear. So don't go and use those addresses, basically, is what I'm saying. So anyway, past that, because A has matched something with inside its ARP table, it can then populate that destination MAC address in its actual data that it wants to send, and it can send it on its way down towards the switch in this situation. That switch has already heard traffic from A and it's already heard traffic from C, so its MAC address table is already populated as well. It knows what interfaces map to what MAC addresses, and vice versa. So it says, okay, I'm trying to forward this packet to all C's. Well, all C's is behind ETH1.3, which is this physical interface here. So the switch is probably going to refresh its cache for the MAC address all A's. Just reset a timer, make sure that it doesn't time out, so then we still retain that state. It's then going to forward it out, and then C is going to end up receiving that traffic. It's then going to know that it's destined for it because it looks at the layer 2 information and that actually matches its physical details. So that's normal operation. So hopefully that makes sense. Now, obviously we talked about layer 2 data flow, and that is purely with inside, let's say, this segment here, this, let's say, tech network. It's between traffic between D and F or E, for example. It's not dealing with how we can talk between D and A, for example. And that's where layer 3 comes involved. So we have a range of IP addresses that we can use to address these devices, so then we can reach them over a wider network, over between devices that can actually process at layer 3. So we have unicast addresses. So yeah, we have a range of addresses for different use cases. So we have a unicast address, and that concept is point to point between one host and one destination. So in that previous example, it's A to C, for example. And those IP addresses are to specify one single destination host or source host, right? We then have broadcast. So as we mentioned before, if that switch was very dumb, it didn't know anything, it would just flood out traffic to the rest of the layer 2 network. Now that's great in some situations, and there are some situations where an application actually really needs to do that. So you can take ARP as a good example of that, but we're looking at IP addresses. So I don't know off the top of my head a good example of where you want to broadcast to your whole local layer 3 network, but it is possible. There is an IP assigned at the end of your subnet range, and we'll get on to what subnet ranges mean. But there is an IP address at the end of your subnet range which is assigned for broadcast. It isn't a well-known thing across a network that this explicit IP address will always be your broadcast address, but it's generated based on the size of your subnet. And I'll get onto what that means in the later slides. There is then multicast. We should all know what multicast is. We've probably all heard of it. Some people might not fully understand it, but we'll talk about multicast in a lot more detail in a later topic. But all you need to know for now is the multicast addresses are their own specific reserved space inside the IPv4 range, and they're specifically used when you are trying to address a group of end hosts. So that is traffic between maybe one or maybe multiple devices to definitely, usually, multiple end devices. And so those addresses are very specifically utilized and reserved for those destination addresses. So we can send traffic from one source to multiple destinations. A very good example of that is media traffic. If you want to send a video stream across the network to multiple different devices, instead of sending a stream from 5 streams, unique streams from one device to 5 end devices, you send one stream from your source, and then the network beyond that is then going to replicate that as required so that you don't have overhead on your original source. But yet again, we'll talk about that in a little bit more detail on another talk later on. So, layer 3. We obviously have that understanding of what IP addresses are, where we can use them. But how does that flow of data actually work? Now, it probably makes more sense to look at the format of the addresses, but I think to understand the format of addresses, you kind of need to know the flow. So I've chosen to start with the flow, and I'll try and keep it relatively straightforward so you can follow along. So small little bit of an internal office diagram, let's say. You've got a technical network, you've got a lab network, and then you've got a sales network. These all have different what's called subnet ranges or subnets. Now, that concept of a subnet is a grouping of end hosts or addresses that can be represented by one IP address. And so that's really important when you're dealing on wider scales. In this situation, we've got only 9 end hosts in the network. So that's fine. If we stored in this router 9 entries for those devices, that's fine. No one's going to complain. The router's going to be fine and it's going to work for days. But let's think about this in a bigger scale. If this was, a data center, if this was the wider network, internet, we've got millions, billions of different addresses on the internet, on networks across the world. And just imagine if we need to, we're working on the internet, we're a core router on the internet backbone. And we have all of these different networks around the world that we want to reach or we want to provide reachability to. If we were to store an entry for each one of the possible endpoints on the internet, well, that would be crazy. That device would have to have a lot of memory and a lot of storage to actually store that state, store that information, and know which path it needs to take to reach whichever end device. Now, instead, what we do is we group those IP addresses. So in the case of, D, E, and F, all of these have a relatively similar address. They all start with 10.12.2. And so they can be summarized by that very similar address, 10.12.2/24. And I'll get onto what that /24 means in a few moments, but it's identifying effectively a range. And that range in this case of a 24, and I'll explain where we derive this from later, but that can be from 0 to 255 in the very specific case of a /24. And that means from a router's point of view, if you're trying to reach an IP address within inside that specific range of addresses, well, you just send the traffic out of this interface here, and then you eventually get to it somehow based on the layer 2 networking. Where this IP addressing then starts to play dividends is where you have bigger networks. So in this situation, all of these addresses start with 10.12 in some aspect. Well, this router can then just advertise an address of 10.12. And any upstream routers just then have to store one bit of state for all of these 9 devices, rather than 9 single entries when they've got maybe hundreds or thousands of different endpoints that they're trying to provide reachability for. So that's a bit of an insight into how we use subnets and why they're used. But they're also used to be able to allow us to know when we need to escape our local layer 2 domain. So let's take the case of device A. If device A wants to reach device C, what we need to do is we just need to stay within inside our local layer 2 network. This is all within inside one layer 2 network, so you can address it using those physical addresses. This switch doesn't really care about IP addresses. You could send a piece of traffic without an IP address, and this switch technically probably would be able to forward it. I've never tried, obviously, so don't take my word for it. But in theory's point of view, that switch will only ever look to that layer 2 portion. And so because this device is reaching something within inside its local layer 2 domain, represented by these dashed dots, right? We don't need to deal with IP addresses. We don't need to leave our local subnet or our local range. However, if A needs to reach D for some reason, we do need to leave our local subnet. And we can tell that by looking at the IP addresses. So we're currently 10.12.3 something, in this case .30 in the case of B, and we're trying to reach 10.12.2.20. Well, that's slightly different at the start. That's a slightly different range. If we look at the actual address that's given to this range, it's 10.12.3. However, this range is 10.2. So sorry, 10.12.2. So that's a different range. So we know that we need to escape our local layer 2 network. And I'll talk about how we know that a little bit more once we go into the details of the address format. But that's a concept that we have with masking or subnet masks. And when we know that we need to leave our network, well, we have a thing called a default gateway. And what that default gateway says is, if I need to leave my local layer 2 portion, well, I need to go towards the gateway. The gateway is going to be my way out of my layer 2 network. Very much like, if you want to talk to someone with inside your office, well, you just go over and walk to them. But if you need to talk to someone else in a different company, pre-COVID times, obviously, you would leave a door, you would leave a corridor, you'd leave the building, you would go and get in your car and drive somewhere and then get out, and then you would walk into their office. So you can imagine this local layer 2 network as an office space. And then this, you're leaving your office space into then some kind of medium between that office space and someone else's office space, which would be the layer 3 network. And you're going through that to then get to that end destination layer 2 network, where then you can find that relevant person within inside that office space. It's a random analogy that I just thought of, but hopefully that makes sense on how this kind of works. Now, we have that concept of that default gateway, which in this situation is the interface on that router. looking back at that example, terrible example, your default gateway would be the main door of your office, for example. You would head towards that to leave your office space. So very much similar. If A wants to reach G, it needs to leave via its default gateway. It needs to leave via its exit point of its local layer 2 network. And that default gateway can be any address inside your local subnet range. As long as it's defined and as long as those end hosts know, then they can send their traffic in that direction. Yet again, it's inside the layer 2 network, so you can use those physical MAC addresses to then hit your router. Your router then does the layer 3 network. It knows where those IP addresses are found, and it can then forward the traffic in that direction. So that's how you would flow the traffic across the layer 3 network. Obviously, I haven't shown a bigger topology, but hopefully that gets that concept, flowing traffic between different subnets and why and how that happens and how we detect that. Coming back onto what I've been talking about with the address formatting, this gets a little bit more complicated and you've got to think slightly differently. If you understand binary, this will be a piece of cake for you. If you don't, well, maybe not. But this isn't a binary class. I'm probably not the best at explaining it, but I'll try my best. So IP addresses are built up on 8 bits, what's called bits. Each bit represents a 0 or a 1. And as you go inside your 8 section, your 8 bits, this represents a bigger number as you go. So this represents 1. If this was then a 1 here and a 0 here, well, then that would represent 2 and so on and so forth. Yet again, it's not a binary class, but hopefully that just quickly refreshes anyone who completely forgot about binary. So IP addresses are formed up of 4 blocks of 8 bits. Each one being referred to as what's called an octet. Now that can represent then a number, a human readable number. So in the case of this string of binary, that represents 13. In this string of binary, that represents 56. This 63, this 251. And so that's how we form up that IP address. Now that might seem, very simple. So what? However, understanding that is binary really helps on then understanding how we then define this subnet range or the subnet mask. So the subnet mask is a very important concept as well to understand. And so it can be represented either as a slash number. So in the case of this, /18, as we see here, or it can be represented as the raw figures that would represent the binary. So 255, 255, 192 in this situation. So this comes from this value here of binary representing 255. This value of binary here representing 192, and so on and so forth. This, all zeros, is 0, obviously. Now, what that actually maps against is, well, in the case of the /18, it's 18 bits that are set to 1 and a range that are set to 0. And those 1 bits, where we have set to 1, that maps up against what is called a network portion of your address. And so because we have a set of bits that are set to 1, those represent the network portion. So all of these bits here, which map up to a 1 on the subnet mask, are representing the network portion. So those are the important bits to then pass on to the router, because from the router's point of view, it doesn't care about anything past this point. It doesn't care about this end host portion, which is represented by the zeros. It just needs to know, is the address inside this range? Doesn't matter about anything past this. Do these specific bits match? If they do, okay, cool. Let's pass this down and it matches this specific route, so we pass it out of this specific interface. So that's one portion of why we have that subnet mask. We also have it for defining the space or the range of which end host IP addresses that we can assign. So in this case, we have all of these bits to represent end hosts. So in the case of a /18, we have 14 bits that we can assign for specific end hosts. What that actually means is within inside a /18, we can have 16,400 odd addresses. I don't know that off the top of my head, by the way. There are things called subnet calculators on the internet that can give you this information. But effectively, from these 14 bits, you can represent 16,000 odd different values, and each value can be assigned to a specific end host, meaning that you can have within that subnet 16 odd thousand end host, end IP addresses. And so that's how those IP addresses are formed, and that's how we that's how that subnet mask is actually utilized to then define that range. So we have that network portion, which is really important when we're actually forwarding traffic across the layer 3 domain. And then we have that end host portion, which is really important when we're actually trying to find that end host within inside that, let's say layer 2 domain, or local layer 3 subnet. Both are the same thing effectively. If we look back at this data flow diagram, while this is a layer 2 domain, this lab network, for example, it is also one layer 3 subnet. It's a grouping of end hosts to represent one specific network segment or one subnet. So that's layer 3 addresses. That's the forwarding flow. Now, the last piece that I'm going to touch on relatively quickly and not too much detail, but it's important to understand the concept, and that is VLANs or virtual LANs. LAN standing for local access network segment. Ignore the segment bit. No, it's just LAN. The S here is multiple of VLANs. Sorry. So what VLANs allow you to do is take what would previously be, a single layer 2 domain. So ignore the VLAN assumptions here. A, B, C, and D would be within inside one single layer 2 domain. And that means that A can directly talk with B. A can also flood traffic and impact potentially D and C. Okay, fair enough. How does that matter? Well, let's say D is a very fragile device, which is really old and it can't deal with much extra traffic. If it gets a few extra broadcast traffic, it's gonna fall over and it's gonna crash, and it's gonna take 5 minutes to come back up. Maybe that's a piece of really important equipment for your application, for your business. So what we can do is we can segment those two devices logically speaking. They're still connected to the same layer 2 switch, but we can logically separate them into two what's called VLANs. And those VLANs are virtual LANs. And now the way that we identify those two is via VLAN IDs. So they are arbitrary numbers from a specific range. I can't remember the range off the top of my head. I do apologize. But there's a large enough range that you can have quite a few VLANs within inside one segment. And so this yet again is kind of similar to IP subnetting, but it isn't. To be very clear, it isn't. What it allows you to do is to take a previously existing one single layer 2 domain and split it into two. Now, yet again, if we look back to our previous diagram, this lab network, yes, while it is one subnet, it is also one layer 2 domain. So in the case of these VLANs, we can split these VLANs up, but each VLAN still needs its own subnet. It still needs its own IP range. You can't have them clashing. Otherwise, the router doesn't know which VLAN to send the traffic down. So the way that it works, let's imagine you've got some kind of source here that's trying to send to VLAN 10. VLAN 10 should have its own subnet range, okay? Maybe .10, for example, .10/24. So we have a 24/range of address that we can use. VLAN 20 has .20 as an address, 1012.20 and 1012.10, for example. And so the router itself will see what's called a switched virtual interface, or an SVI, which is effectively like a logical interface. Like you have your physical plugged up, Ethernet or fiber interfaces, it's going to have these logical interfaces, which then it can send traffic out of. And those are going to be given those subnet ranges. So then the router knows, well, this subnet is out of this VLAN. This subnet is out of this VLAN. So then you send them in the relevant directions. Now, what happens is that maybe that traffic goes over exactly the same link between the router and the switch. In that situation, between the layer 3 header and the layer 2 header, we're going to add in an extra header with some extra detail, with some extra control information that can be read at that layer 2 layer as well as at a layer 3 router if you really needed to. And what that's going to say is this traffic is tagged as VLAN 10. This traffic is tagged as VLAN 20. And so when that hits the switch, while it came from the same physical interface, the switch is able to pass that information, that control information, and it's able to say, well, this traffic is intended for VLAN 10. So I'm going to only send it to the hosts that are actually behind VLAN 10, that are assigned to physical interfaces for VLAN 10. And so at that point, if A wants to send traffic to D, well, the switch knows that A is assigned to VLAN 10. So it can't send directly to D, which is in VLAN 20. They are completely separate layer 2 domains. So the switch isn't going to send traffic between the two. Yeah, it shouldn't do, unless you set something else up. Not going to get into that. So what happens is, A is going to send the traffic up to its default gateway because it's going to reach outside of its local subnet, outside of its local IP range. The traffic is then going to reach the switch. It's going to see, okay, this is from VLAN 10. I'm going to tag that traffic. I'm going to send it up towards the router. The router is going to see that tag itself as well. And then it's going to say, okay, that's been received from VLAN 10. Where does it now need to go? I'm going to look at the IP information. Okay, it needs to go to something in the VLAN 20 range. So I'm going to send it back out of that VLAN 20 SVI, tag it, send it down to the switch, and then the switch is going to make the decision based on that destination MAC address. And so that's how we can then separate those logical layer 2 networks down into more functional segments. Hopefully that makes sense. Hopefully that explains how we can then slightly alter those normal data flows that we would normally have, and how we could then split up those layer 2 domains. So I think that's everything covering for today for the fundamentals of layer 2 and layer 3. Hopefully that was useful. And if it wasn't, please let me know. If you have any questions, feel free to let me know and I can try and explain them, and hopefully explain it in a different way that might make sense. Thanks for watching, and I think that's all for today. Thanks.